May just show up a little late. That's okay. All right, so today we're going to talk about ACI 211 mixed design method. So this is very old school. So before we kind of get into the theory behind it, I want to make sure we can do a little math. So today I have a handout that's in front of you to do some of the basic math behind a general mixed design. And we'll go through it. It is pretty basic, but I just want to make sure we're all on the same page. So somewhere, whenever we're talking about mixed designs, people always ask the same questions. Weight and volume. We have to do these conversions. I don't get it. Why are we converting from weight to volume, volume to weight, and what's this all about? Well, you got to remember, concrete is sold by volume. When you estimate in your estimating class, a lot of you are in Dr. Yates's estimating class, so you're estimating concrete by volume, cubic yard. So, contractors, whenever you're going out and building something, you're going to figure out how much volume it is to fill up in your forms. So, the concrete truck comes out, it's a certain volume, pour it out. Well, whenever that ready mix truck, though, it's batched sometimes by weight. Some of the liquids are usually batched by volume, though. So they have to do a little conversion back and forth to figure out just to, get the weights right. But at the same time, you got to figure out when you're batching stuff by the weight, you got to figure out, well, what's the volume? Because your end goal is you want to have enough to yield for your volume that you're looking for. So if you have a 10-yard truck, you want to make sure you have 10 yards you're selling that customer, not 10 1/4, not 9 1/4. You want, 10 yards. And so what you do whenever you're designing a mix is you start off by saying, okay, we're going to design based off 1 cubic yard. And then if we want to make it into 10 yard for a 10-yard truck or 8-yard truck, then we can just times that by 10 yards or 8 yards, depending on what you want. And so if we're doing trial batching, when it's 1 cubic yard, we can even, convert it into 27 cubic feet and then take it down to maybe 2 cubic foot whenever you do trial batches at the lab. And so, and we'll go through some of that too. So, there's some math that starts getting involved with designing. So, it's sold by volume, it's batched by weight or volume, and then usually you want to design it by volume, but you have to have both the batch weights and the actual volume for your design. But your goal is you're trying to, design 27 cubic feet or 1 yard. So like I talked about, think about a 3 foot by 3 foot by 3 foot. That equals 27 cubic feet, 3 times 3 times 3. And then that's 1 yard. So in that 3 foot by 3 foot by 3 foot box, we're going to figure out how much aggregate, how much, coarse sand or coarse aggregate, how much fine aggregate, how much water, how much cement, and how much air all gets put in that little box. So that's what our goal is when we're designing. We're trying to figure out how much to fill up that box with. So if we're trying to figure out the volume, and we know our batch weights, so our batch weight we can take, and we know the specific gravity of the material, and we know the unit weight of water, 62.4, then we can convert, we can know the volume. And we can also, do basic algebra, take this, denominator here, move it over there if we want to figure out if you know the volume. to figure out our batch weight. So, I mean, you can do basic, basic algebra that you learned in probably the 8th, 9th grade to go and go back and forth. So that's kind of what we have here on this example problem, is if you see at the very top, it says example converting weight to volume, and then it says ABS, that's absolute volume, ABSVOL. So the basic equation to figure out the absolute volume of a cubic yard, you have, that's the kind of the basic equation. You have the weight of the material divided by the specific gravity of that material times your unit weight of water, which we're going to assume is 62.4. That's what we assume when we do mixed designs. Obviously, whenever it's dependent on temperature, but that's what we use as a standard. So that's why when you look at this, we look at these boxes here that we're about to fill out, everything already has 62.4 already filled out, because that's what we assume. All right. So we're trying to fill our box. So if you remember specific gravity, like we talked about right before class, it is a comparison of really density. So if you have, the weight at the same, if they're the same volume, and you compare the weight of water compared to the weight of stone, how they get out with 2.7 is there's the ratio. 270 pounds of stone divided by 100 pounds of water is 2.7. So that's how they get that. You get the unit weight by just putting the material in a known volume and weighing it. So pounds per cubic foot. Absorption, we've ran absorption, we've ran unit weight in the lab, or at least talked about it, and tried to figure out, absorption at SSD. So whenever the voids are fully saturated, but there's no free water, so there's nothing on the surface. So let's kind of go through a basic example on the board or on the PowerPoint. So how many cubic feet will a 5-pound bag of Portland cement occupy in our little box here? So 470 pounds divided by 196.56 is 2.39. You might say, I kind of should have probably put this a little bit better, but what is the specific gravity of cement? It is 3.15. So 3.15 times 62.4 is 196.56. So that's how they get the bottom number. So the top one's just here in the given. So you do that together, that equals 2.39 cubic feet. So you pretty much do the same thing through the process, except for air. And we'll talk about air here in a minute. But you figure out what your specific gravities are for each of your materials. And if you know your weights, you can convert to a volume. So if this is our example, you have the graph or the worksheet in front of you for people that are online. This is the worksheet that I think I have attached in the lesson. But we have our weights. So we have a given weight of cement and the specific gravities of it. And it goes all the way down. So if you fill out your boxes from that worksheet, weights are on top, are on the numerator, and the specific gravities are on the denominator on that box. Okay. So wait for a second while you fill it all out. And then when we get to air, it is 6%, you know, and it's times 27. So I'm gonna look to the next one, which is the worksheet already filled out. So we should have, so people do math a little differently. You may want to do the denominator first of the thing on bottom of the fraction. So 3.15 times 62.4, which equals 196.4, something like that. And then you take 564 divided by that. So, you know, there's different ways. You may have a calculator that does the parentheses for you, so you can type in 564 divided by parentheses 3.15 times 62.4. So a good way to check to make sure you don't mess up is all your numbers should be below 27 cubic feet. If you have something that's above 27 cubic feet, then you probably did something wrong, okay? So you can do the same thing for your stone. Same thing for your stone, 1800 divided by, you can put a parentheses. Most of us have a smart calculator. I mean, this is basic 5th grade math that you should have probably learned in 5th, 6th grade. So it's not complicated. The complicated part is remembering everything. There's a lot of little details that we're going to get into. So how do you get the 564? How do you get the amount of cement? How do you get the amount of stone? Okay. So 6% of 27 cubic feet is 1.62. When I teach it, there's always at least one person in the class. It's like 6% of 27 is what? And so a lot of times you want to do 6 times 27. No, you got to convert it into a decimal form and multiply it. Okay, I know that might be silly for some of you, but there'll be somebody that will do it every time I teach this. So everybody following me, I hope you're like, this is really dumb, some of the stuff that just came out of your mouth. We know how to do basic math during college. I hope that's what you told me. It's hard to see whenever you just have, when I just can read your eyes. So you're wearing a mask. Kind of weird, but this is where we're at in life. So everybody finished this handout. Okay. So this is the basic math to do it all. So I always hand this out when we do mixed design calculations because this is kind of the process. Kind of gets you the warm up. Air is a little different because it's a percentage. 5% air, that's what it means. 5% of the volume of the concrete needs to be air to provide freeze-thaw durability. So the volume of that for 6% is 1.62. So, you know, some of the basic homework problems will be stuff like calculate the air volume of 5%. You'll have that. So real basic stuff. At least I hope so. If it's not, I apologize. I'm not trying to, you know, but maybe I'm just not connecting the dots well enough for you. And please let me know if I'm not. But again, basic equation up there, you run through the steps. And so you have all this here. So this whole entire column better equal 27. So if you add up each of these, it's going to equal 27. If it doesn't, you did something wrong. Okay? So it should equal 27.00. Maybe you didn't, maybe it's not 00, but it's pretty close to, 0.0 something. Sometimes when I do it, rounding errors can kind of mess up. So it's not unheard of to have 27.01 or 26.99. Don't get too caught up in that. You made a mistake if it's 27.1 though, okay? There's something wrong, or your mix is over yielding or under yielding if you're off by 0.1 cubic feet. So that's kind of, when you look at a batch ticket and you have your batch weights on the left-hand side, the specific gravities, and then you have your volumes. So if we have a 3 times 3 by 3, again, this isn't perfect to scale, but I think we can all kind of understand how much material that fits in that box to make, 3 times 3 times 3, so 27 cubic feet, so 1 yard. So that's kind of how, the basic math behind it is. So today we're going to talk about ACI 211 mixed design method. And I don't know if I got to it in the last PowerPoint. Maybe I should have added a couple slides, but who in here eats steak? Okay. Do we all prefer all medium well steak or well done steak, or we're all, probably every single person in here likes different degree of pink. You like steak. Some of you like it burnt because it's good to your teeth. Some people like it where you literally, it's as bleeding as possible, where they barely even put it on the grill and just flipped it a couple times just to make the little marks. And that's some people are happy with that. Well, there's different degrees. And so in the real world, after you get out of the classroom, it's kind of how mixed designs sometimes are, where people prefer one mixed design method to another. So ACI 211, some people, I know people on the committee they follow this very strictly. I also, there's people like me that have other mixed design methods that they use that work a lot better for me, that stuff I prefer, and a lot of other people prefer it. I get emails from people from Australia and South Africa, Europe, different places that prefer the mixed design method that I've been working on. And so, people just prefer different things. But so we're going to cover 211 and what 211 is about. There's really 9 steps. And I meant to bring the book for it. Sometimes people, when they teach this class, they'll supply that book. Like I said, it was made in 1991. Anybody born before 1991 in here besides me? Yeah. So that's the last time it was updated. That's what I'm getting at. This thing's very outdated. And I want to talk about why it's outdated. But this is the method people use still. It's on for the construction PE exam, professional engineering exam for construction. This is on there. So, it's part of it. So the information for designing a concrete mix. Really, you need all this information. I didn't get every single step when it was on here, but I will. I will put it on there on the final PowerPoint, but you need to know kind of a slump. You need to know if your concrete's going to be air entrained or non-air entrained. You need to know a compressive strength value. The specific gravity of the cement's always 3.15. And then you need to know your aggregate information. So the maximum coarse aggregate size, you can either calculate that, or they'll use, a lot of times people will just assume 57 or 67 stone for gradation. Everybody in here hopefully should know what that is, since we just had a test over it. We had a lab over it where we ran gradations. And then we did dry rotted unoweight in one of our labs, and we talked about how to calculate fineness modules, right? Had another lab talking about specific gravity and absorption. So all this stuff we did in our lab. And that's just aggregate information. So the different testing behind it, you know, we kind of went over, or we did in class. So that information a lot of times given to you, but it's important to know what it is. So this is the ACI 211 mixed design table. I rewrote it because it was hard to read in the copy I had. But the most flowable concrete they have is a 4-inch slump, maximum slump for their concrete. So back in 1990, it was actually written before 1991. So, you know, because it takes a little while to go through. So back in the 80s, they didn't have a lot of, you know, admixtures. They didn't really use a lot of fly ash. That was just kind of coming out. So workability at a 3 or 4-inch slump was really generated by the amount of cement and water that you were added to the mix. And a lot of times people focused on the amount of water. So engineers really wanted to limit the amount of water you had in your mix. But today, when we do a floor slab, a lot of times you're at a 5-inch slump, not a 3-inch slump. If you do residential work, you know, it's almost self-consolidating. You know, they want a 8, 9, 10-inch slump. They don't always want to pay for an 8, 9, 10-inch slump, but that's what they want. They want it to flow like water. Oh, you ran slump in the lab. You measured a 3 or 4-inch slump. That's not water. So, you know, and beams is the same way, a 4-inch slump. The minimum's a 1-inch slump. So there's kind of a range, but that's just the recommended table. We'll talk here in a minute. I'll show you another table where some of this kind of puts together where we actually start selecting water and stuff from it. Well, you can kind of go with other ranges. That's just they're recommended from, you know, from back in the day. And you can, you know, kind of pick your own slump depending on what application you're in. So step 2, after you figure out what slump you have, and you write that on your piece of paper, the next step is figuring out your maximum size of your coarse aggregate. So there's 3 big criteria for your maximum. Nominal maximum is what we're going to use in this class, okay? Not the maximum size, but they use it interchangeably. Nominal maximum size. So, you know, it's either going to be 57 or 67 stone we're going to use. So, you know, either a 1-inch for 57 or a 3/4 inch for 67. And then the largest nominal maximum size shouldn't be more than 1/5 the minimum dimension of any concrete element. So 1/5, you know, whenever we're looking at a different concrete element, the dimensions, if it's if it's 5 inches thick wall, then, you know, 5 divided by 5. So, you know, you don't want any more than 1 inch. For a floor slab, say it's a 6-inch floor slab. So 1 divided by 3 is 2 inches. So most concrete's placed in the United States, I would probably guess at least 80% 4-inch slab. So Ethan, you have a calculator in front of you. What's 4 divided by 3?
1.3.
1.3. So you can get away with using
a 57 stone, not a 467 stone, but a 57 stone, you know, with a 4-inch slump or a 4-inch thickness. You know, you also have rebar clearance. So in between your form work, between your rebar and your form, there's got to be at least, you know, 3/4 of the clearance. So you just kind of have to be aware of that. You don't want rocks getting stuck in there. So there's kind of a clearance between it. So how, like I said, if you didn't realize, if you forgot, I know you have slept, there's been an exam, some of you are like, all right, I can forget all that material. You forgot. So for a 57 stone, 1-inch nominal maximum size, for 67, it's 3/4 of an inch. So step 3, so after you figured out your slump, you figured out your nominal maximum aggregate size you're going to use, which again, a lot of times it might be given to you. You're going to determine the water and air content. So how you do that, is it entrained air or no entrained air? This ugly table, the top part is non-entrained air. So non-entrained air. So no air is added. There's no air, then you figure out your slump. Maybe you have a 3 to 4 inch slump. If you're trying to do a 5-inch slump, you can't do it because there's only 4 or 6 there. That's a joke. But again, another misprint. Then you go and you figure out, okay, we're going to use a 1-inch aggregate, and maybe it's a 4-inch slump, so 325 pounds of water is what I'm going to use. If it's air entrained concrete, okay, well, I need to figure out, I should also say with no air entrained concrete, there's going to be some entrapped air in your mix. So with a 1-inch slump, they're going to assume a 1.5% entrapped air. Okay, that's really important. So even with no air, there's actually air in your mix. With a air entrained concrete, say a 4-inch slump, you can actually go and figure out, okay, well, I'm at 1 inch, I can go down, I can get away with a little bit less water, to say it proves the workability. So 295 pounds of water is what I can get away with a 1-inch slump, or a 4-inch slump, and a 1-inch nominal maximum size. You can also figure out your minimum exposure. So a lot of times I'll just provide you with a %, but if you want a minimum, in this chart they have recommended. So you can actually go down here and figure out, okay, so I'm at 1 inch, and I'm at a moderate exposure, so that's 4.5, or maybe I'm at a severe exposure, 6% air. So that's kind of how they do it. I talked about how to design, how to get better numbers than this. With the durability, what they have for actually the specifications for concrete. So I don't really recommend using this. And most of this in train I'm going to actually give to you. So you're going to assume either usually a 1.5. That's usually a pretty good number, but I'll probably give that to you. So step number 3, then you got to figure out your water cement ratio. So again, air entrained and non-air entrained concrete. Where are we at? And then, what was the compressor strength? So if you're at 3,000 PSI, no air, it's 0.68. You're at 3,500, it's going to be in between these two numbers. All right, so The next step, after you figure out your water to cement ratio, you can kind of start putting stuff together. We just determined our water content. I went through the, 295 pounds for a 1 inch, or a 1 inch nominal maximum size with a 4 inch slump, or 325 for a 4 inch slump with no air entrain. So you can actually take that number, you have your weight of your water divided by the water cement ratio. So we talked about 3,000 PSI, having a 0.68 water cement ratio. Again, this isn't for durability, this is just for strength. It's really important to realize that. Obviously, durability requirements may want something much lower than a 0.68. But this is, again, the ACI 211 mixed design method. That's what I'm teaching today. So where are we at now? Well, we talked about, this is just an example. We had 6% air. Great. So there's your air volume, 1.62. Maybe we wanted 250 pounds of water. Maybe we found that from the table. Great. So we have our volume. And then we back calculated our water to cement ratio with our water content to figure out our cement. That's what step 5 was all about. Taking the, weight of water, the weight of cement, that's water cement. Real basic. So so now we're at the aggregates. How we get our rock, how we get our sand. So step 6, you use either one of these tables. So this is the figure, this is the table. They're the same thing. One's just visual, one's this tabular, so it just has the numbers. Some people prefer one or the other. It truly doesn't matter. It's just use one of them. But both of them have the same thing. They have a nominal maximum size. So nominal maximum size here. Actually, this is the metric. So nominal maximum size in inches. Nominal maximum size here. And then you have a bulk volume of dry rotted coarse aggregate per unit volume of coarse for different fineness moduluses. What in the world? So this is your fineness modulus of your sand right here at this table. Or each of these lines has a fineness modulus. So this is coarser sand, so this is 0.30, and it goes up to 0.24. And so what you do is, if you know your fineness modulus of your sand, and you know your nominal maximum size of your coarse aggregate, so this is your rock, this is your sand, you can go through and figure out how much coarse aggregate you need to fill your volume. So in essence, you can think of this as, it's almost like a percent of the volume to fill up that little box we're talking about. In essence, that's kind of what it is: bulk volume of dry rotted coarse. So if you have a 1 inch and a fineness modulus of 2.60, your bulk is 0.69. You do the same thing here. You've got 1 inch, 0.6 is the red line, and then you can actually go over and figure out pretty close to 0.69. So if you're not, or you're not right at 0.60, then you need to interpolate. So I like using the table because the numbers are there, but some people like the visual, whichever one. Okay, then what do you do with that number, that bulk volume number? Well, what you do is, again, it's the volume percentage of your coarse aggregate. So if the whole thing was filled up, dry ready unit weight, pounds per cubic foot, we can figure out how much needs to actually be in that. So pounds per cubic foot, well, this is in pounds per cubic foot, so we need to times it by 27 to convert it to a cubic yard. And then we can take it and say this is how much percent of coarse aggregate that we're going to have. So if we, like we said before, if it was 0.69, then it would be 0.69 times maybe 110 pounds times 27, and that would give us our amount of coarse aggregate that we have. Again, this is just kind of an example, 1,800 pounds of rock, and then you can convert that. You can take that, so you can convert that to your actual volume too. So how do you get sand now? Well, believe it or not, they say, you know what, sand's a filler. So it just needs to fill the rest of the volume up. So they just add up all this. Then they 27 minus, that. So the top equation here, 27 minus that total volume equals the volume of fine aggregate you have. Then you take that fine aggregate number right here, times by the 27, times 62.4, and that'll get you your weight of your fine aggregate. So if you kind of got confused with
the specific gravity, 0.7, specific gravity, the gravity that.
Specific gravity is the specific gravity of the fine aggregate. And then and so for this equation here, we're just inverting it. So we took so we know our volume of our fine aggregate, which we got up here. And so we just took our specific gravity and our unit weight, the denominator, we moved it up here. And we just multiplied all three to get the weight of the actual material. So just basic algebra. And that's how you get that number. So then step 8, you adjust for moistures. So again, you want to be at SSD. That's what we design at. Whenever they wrote the standard, they actually designed it at, they talked about being completely dry. That's actually incorrect. Even some of the numbers they use, if they're using specific gravity at SSD, then they should be here, not there. So if you use specific gravity at dry, it'd be over there, but that's not. Anyways, we're going to change it. We're just, but we'll use specific gravity at SSD. So we want to figure out how wet our rock is. So we've done in our lab. I showed you a video how to do absorption. So absorption is, at SSD. So how much water gets absorbed in the rock. We also figured out how much moisture content altogether. So if you want to do math to figure out your adjusted moisture, if you have, if you batch 1,830 pounds of rock, so 1,830 pounds, so that's what this number is. And you have an absorption of 0.5, moisture content of 0.29, so 2.19 minus the 0.5 gets you this right here. Okay, so 2.19 minus 5.5 will get you this number. And whenever you actually calculate that 1.69, when you figure out how much water is actually in this, it's actually about 30 pounds. So it's about 1,800 pounds of rock and 30 pounds of water whenever you go to batch 1830. So with that mixed design example I talked about, where you have 1,800 pounds of rock, you actually need to batch an extra 30 pounds to compensate for that water. And I'll go through in much more detail about how to compensate the entire mix design, including the water, on a different day. And then you trial batch. So it may look great on paper, but I don't know how many times I said I'm not dragging that. I don't know what that is, but that is not what that was not the specs. That's not a, it's a 0-inch slump, not a 5-inch slump like I asked for. You can also go out and test it. So we can do this in the lab and we can test all those things well before it goes on the job site. So a lot of times we do trial batches. People even get a ready mix truck out and they'll batch a yard or they'll batch 4 yards. And they'll just see, what it looks, how well it works. So those are the kind of the 9 different steps. Figure out your slump, you write it down, and your maximum coarse aggregate size, you write it down. And then from there, you can actually take those 2, figure out your water content. And you can figure out your air content on that table too, or it can just be given to you. And then you figure out, after you figure out your water content, you can go through and take your strength number, figure out what water cement ratio you need to be at. Then you can take your the water cement ratio, back calculate it to figure out what your cement content is. So water divided by cement, weight of water divided by the weight of cement. You can take you can multiply it, the water cement ratio times the weight of your water to get your cement content. So basic algebra to get there. May have said that a little confusing, but if you look back at it, you're like, okay, weight of your water times your water cement ratio. Maybe just cement. Okay, cool. Basic algebra. Step 6, you go through, you can either use the table or you can use the figure to get a bulk volume, so a percentage of the volume of the rock that you actually are going to use. So you'll use the nominal maximum versus the fineness modulus, or you use the graph with the nominal maximum up here versus the different graph curves. Figure out your course content. And then you can go back and times, that bulk volume number times your unit weight times 27. And that'll get you your course aggregate content. And then you say, okay, well, I know air, I know water, I know the cement, I know the aggregate. 27 minus all those different volumes gets you your fine aggregate content, because we treat it as a filler in 211. And then the other 2 steps are, okay, now we need to adjust for the water that's in our rock. And then we did trial batch it. So problem with that, this is the very last slide. We use fly ash, we use slag, we use water reducers. In fact, probably over 85% of all the concrete used in the United States has a fly ash and a water reducer in it. The method does not cover either one of those. Also, there's lots of water adjustments that you need to make. So the method's broken in a lot of ways, but it's a starting point. So with that, I will let you guys, sorry I went a minute or 2 over, but please let me know if you have any questions.
Will we get some information about the lab, or finish it, the lab from yesterday?
Yeah, I'll just email you.
I mean, okay.
Yeah, I'll email you about the lab for yesterday. If anybody has their receipt for their lab manual, let me know.
You're wanting a report for this last slide, right?
Memo?
We'll have both a report and a memo, but next week's just a memo.
Okay.
And then we'll break a cylinder. And then the week after will be the report. Okay? It's all on the syllabus, it's all on the table.